Hey everybody, welcome along to the last session of the day. Apparently we are the people that are standing between you and drinks, but you all look like a bunch of very serious and sober people, so you won't mind if we hold you back a little longer. Anyway, we'll try to keep on time. So my name is Brendan Buffler. Most people just call me Buff. So I lead our research computing team here and at AWS, and we've got a few interesting things to show you today. So I'm going to be ably assisted by Ralph. Ralph's one of our senior solution architects in the public sector team in Germany. So unlike me, Ralph speaks German, certainly much better than I do. I can count to 5, and so I hope you'll forgive me for speaking English at you for the next hour. And we've also been assisted by Scott. Scott's one of our specialist solution architects, Wave Scott. Scott is he's a recovering university professor, aircraft designer, used to work for NASA, for Boeing, and a bunch of other interesting places, and he's done a lot of CFD in his career. So, and he also owns a half-built airplane, which we'll get to at some point. Now, for the first thing we're going to do, I'm going to hand over to Ralph to just to get something running. It takes like a second or two for PowerPoint to give up. So just what Ralph is actually doing is he's about to launch an HPC cluster.
Yeah, so actually you don't need to understand what's happening right now. You should just need to know I'm launching a cluster right now and just enjoy how easy it is. So we'll give it a name and a little bit of options we have to give here.
Put in a 0-sider so that we can get access to it when it comes back up.
Okay. And now maybe the more interesting part for researchers here.
Anybody in here an HPC user already? All right, cool. So this is an awesome bit. Choose your scheduler.
Yeah, so pretty much every interesting schedule is already predefined, so you can just choose the one that you want to use. And well, then let's go down a little bit to our nodes that we want to start. So we have the head node around here, and we have the compute or the worker nodes around here. And just to let you know about the options that we have, take a look at that awesome list of instances. So you're really able to pick the worker nodes that you need for your specific workload. So you need vast amount of RAM, then choose maybe that one here with nearly 500 gigabytes of RAM. You need a lot of CPU power, then choose one with a lot of CPUs. Go for GPUs, whatever you need for your specific workload. Just go there and pick the right tool for the job.
When I used to build supercomputers for a living, one of the hardest things about that was actually you had to try and analyze an absolute ton of workloads and try and understand what was going to be the node type for your cluster that you had to squeeze everybody into so that everybody got that homogeneous experience. So it's actually really cool to be able to design a cluster on the fly for a workload, and then if the workloads need changes next week, you just change the cluster.
Yeah, and that's two other parameters that we will have a look at. So the one is the number of worker nodes that we want to start. So it's just 4. It's a little demo cluster that we want to start here. And there's another one, the maximum number of nodes, and we'll also keep it to 4. We could scale up, so in case your job queue gets larger, actually the cluster could automatically scale, but we don't need that here, so we will stick to the defaults here.
That's another totally weird thing, the idea that a cluster expands and contracts to fit with the jobs that you've got in a queue. So
now we're going to go to the next step. We can also get some tags in here. So in case you have a lot of clusters running and you want to somehow assign them to project teams or whatever, or just give your opinion on certain things, you're able to tag some labels on your clusters. And then we are
We could spend the afternoon telling chemistry jokes. I think that would actually be kind of neat.
And there's just one checkbox that we have to tick here. And now the magic is happening in the background. So we will start up a cluster now. Yeah. It will take a couple of minutes. So we are going to switch back to the slides and come back to the cluster in 10 minutes or something like that.
Thank you. So my team's job is to make sure that we get scientists thinking about science, not servers. Like that's a bit of a mindset change when we first engage with a lot of the members of the scientific community, because most of the time we've always been trying to build infrastructure and then squeeze workloads into it. In this case, we actually work it around the other way. We do the Amazon approach, which is we talk to the customer, understand what their needs are first, and then we work backwards from that to design something that fits with that. So, really, our gig is to be the people to get this message across. The biggest thing here is that we actually think that the infrastructure that most scientists need are these things. So data sets, tools, and techniques. It's not boxes in racks. That's a solved problem. The actual problem we need to solve is how to get this stuff in the hands of scientists quickly. So we run Amazon on this principle of doing a lot of experiments, right? And experimentation is an iterative thing. So the big secret to the Amazon innovation machine is that we quickly keep up with what our customers are doing and we iterate often, right? We do a lot of experiments. We're willing for some of them to go wrong. And as Andy says here, with the real trick is just being able to keep the cost of failure low so that we can do a lot of experiments. We think that science, should be powered by the same thing, because in fact, really the scientific method is just an expression of that purpose, right? Which is, we form a hypothesis, we make a prediction with it, we test it against the universe, and then we see what the results are, what the universe tells us about our theory, whether it's good or bad, and then we recycle that information through our model again, and we just keep going and going and going. Every time we do a lap around this, we get closer to the truth, right? And so, in fact, the hardest thing in science is actually getting around this thing fast enough. Probably the biggest barrier we see at the moment in most science workloads is this experiments and results part, where where scientists actually have to think about the results, where they have to do an experiment, particularly today when a lot of the work that they're doing is simulation-based. So we have a lot of customers doing things like CFD, and we'll show you some CFD happening this afternoon, some computational fluid dynamics. If the computer is the place where you're doing your experiment and simulating a thing, and then looking at the results that come out of that, analyzing how it fit against your model and so forth, then getting access to a computer is actually really the hardest part. So, but there's a little dirty secret in the middle of the scientific computing industry, and I talk as a recovering scientist, that we have this very strange way of doing computing there, and we actually still think, if you look at HPC, it looks kind of old-fashioned in many respects. It's bleeding edge, but it's old-fashioned. So we don't listen to music by going and finding a bunch of MP3 file objects that are stored in an S3 bucket, streaming them back to our laptops and spitting it out through a speaker. What we do instead, it's theoretically possible. What we do instead is we pay $7.99 a month, and we get access to Spotify, even if it does have some pretty questionable music. When we want to send email, we don't send email by telnetting to port 25 and pumping SMTP commands in there, right? We do this instead, right? We use our phone, we use a nice app. When we do this makes us more productive. Weirdly enough, when we actually get to HPC, we actually think this is a really cool thing. And so at the core of HPC, one of the hardest problems we have to solve is to be able to give scientists access to these really powerful techniques and tools, but in a much more meaningful and easy way. So we have to get rid of a lot of the barriers around access to resource when they need it. But we also need to make the software environment better. So that's the mission that my team has, is to try and work out how to make that a better experience. And we work with a lot of partners and a lot of community projects to see if we can get that stuff furthered along. So we're going to be kind of ambitious today and show you 3 software tools that do exactly that. So this is really where where HPC is kind of stuck in many respects. Is back in the 1970s. So the real questions that we have to address is, are we solving the right problem? So in the most common scenario, an HPC site is presented with this kind of problem. They have a fixed number of CPUs that they own over a fixed period of time, and they have to fill up this box. And really all of those colored boxes inside this panel are cluster users. They're people who've got jobs to run, different shapes and sizes of jobs. And so it becomes a packing problem. It never quite works out like that. It never quite works out to be an exact fit, because typically you're trying to plan the allocation of a cluster several months in advance. The only way to actually get this box to fill up perfectly, because some people won't turn up, they'll get discouraged because they didn't have access to the machine when they needed it, or their experiment didn't work, so they don't have any data to process, so they don't need it this week. So the only way that we actually maintain keeping this box full is most supercomputer places, most HPC centers actually oversubscribe their clusters. And so they'll run it at around 120, 140% oversubscription, which actually then means you've got a queue, and that queue means that people have to wait. And so it's almost inevitable that this kind of weird outcome comes about. What we notice when we take away those constraints is that people come and go in a much more different pattern, right? And so the reason this is useful is that if you're a scientist and you can get access to the resource now, not a month from now, then you can seize the moment, you can get some work done. It actually moves you more quickly to being able to iterate on your experiment. So if your iteration cycle is really short, then you can actually iterate much faster. You can get closer to the truth more quickly. So again, that scientific method flywheel starts to spin around faster, and you get to your next discovery sooner. So in the previous slide, you'll see this guy here at the top in the middle, number 7, right? What they actually really wanted was access to some compute cores every few days, and they're probably using a cluster to analyze some data coming out of it could be a mass spectrometer, it could be an electron microscope, or it could be a genomics high-speed sequencer. And so they actually need a bunch of cores every few days to analyze some data. Could be coming from another planet, perhaps. In that model, half of the cores that they need are going to be too early and half are going to be too late. In this model, they get access to them pretty much at all of the times that they're looking for, because they're actually not bounded by the constraints of a data center. So first, I guess we have to make sure that we're actually still solving the same problem with the infrastructure we're building. So with that thought, Ralph's just going to actually get into our cluster now and submit a job. This is the cluster that we built a few minutes ago. You want the blue terminal?
Oh, where is he?
No, you don't want Chime. That would be bad.
Oh, okay.
There you go.
So
the cool thing here is that we built that cluster about 10 minutes ago. We've got instant gratification, right? So we can actually go into the cluster now and we can start submitting jobs, which is what Ralph's going to do. So this is a bit of software from a partner company called Alsa's Flight. We'll talk about it a bit more as we go along. So anybody in here ever done any computational fluid dynamics? Cool. So what we're actually doing here is we're actually just installing. So we've got a bare naked cluster. We're actually installing and bringing up our OpenFOAM environment. OpenFOAM is a really popular CFD code. And then we're just going to do, you can see what we're going to do here. Here's our batch script. And
yeah, so actually that's just what we've seen on the slides a couple of minutes before. So I went into the head node and just installed a module. Now this is our script, our job script that we want to submit, and it's pretty small, pretty uncomplicated. So we're gonna roll out a job on our 4 nodes that we have just created, and so that's about to happen now. So we have submitted job, and now we can look at our queue, and we can see our job is in the queue. We can also just have a look at our partitions or queues, so we can see we have a partition with 4 nodes here, and this will work on our jobs now. And with that, we go back to the slides.
We could also, you know, in a lot of cases, you know, we could actually, it's a pretty straightforward thing to actually have multiple partitions. So you could have a Slurm running on your login node with multiple partitions, so that you can have a GPU partition, a CPU partition, a high memory partition, et cetera, et cetera. And the cool thing is that none of those nodes actually exist until somebody puts a job in there to call them into existence. So this really is a very dynamic kind of environment. So now, a minute ago, I was actually just pointing out the fact that, you know, that iterative loop may not be running fast enough. If, you know, in most scientific enterprises, they have to do an RFP or a tender. Has anybody in here worked on an RFP before? RFPs are horrible. They're horrible for the people who write them, and they're horrible for the people who have to respond to them. So, but the worst bit about an RFP is that they can take, you know, it can take 6 months, 12 months, 18 months, and that'd be kind of fast to actually get from beginning to end. I was actually at the launch of an HPC service in the UK a few weeks ago, and one of the, you know, because they'd bought some on-prem hardware as well as cloud resources, they'd done it as a hybrid cluster. You know, both us and a hardware vendor were there for the launch party, and the hardware vendor just explained that that we had 128 nodes of hardware, of compute nodes available. But the problem is that all of the people in the audience, in the last 2 years since they had applied for the funding and got the funding, had started to do machine learning workloads. And they didn't buy any GPUs because 2 years ago, machine learning really wasn't a thing. So you know, all of the people in the audience were actually not going to use any of the hardware they'd bought, and they were going to use all of the cloud part of this infrastructure. And then the other thing that we also have to recognize is that hardware moves in leaps and bounds, and so we have to make sure that we're actually focusing on the needs of the end scientist, because the hardware moves in leaps and bounds in terms of performance improvement, right? But humans don't, and sometimes the humans are actually waiting for the machines to catch up, sometimes the machines are waiting for the humans to catch up. Right now, we're absolutely in one of those cycles where the humans are not keeping up with the techniques and the capabilities that they need in order to exploit the hardware that's out there. So optimizing for a synthetic benchmark actually isn't the solution to what most of these customers' problems are. The other thing is we also need to actually keep an eye on who our community is. You know, our scientific community is sort of really broken up into this very small, little, thin group of people who know how to use HPC, and then all these other people, pretty much everybody else, right? And that's more or less the division between these two parts. We actually find a lot of, you know, when we talk to our scientific users, it turns out that most of their research starts on their laptop and it never escapes the laptop. So the driving point behind all of this is that we actually really need to get all of these techniques and package them up in much more simple ways. And we think that's going to happen, you know, much more easily in the cloud. The other thing that we also need to think about is scale. How can we immediately, you know, get a researcher's workload and do their first scaling step? For most researchers that are sitting in that small end where their research is trapped on their laptop, they need to be able to do their first scaling step. And the first scaling step doesn't necessarily need to be an HPC cluster. It may well be doubling it or quadrupling the data that they attack or the problem size. And that first step can actually be done pretty comfortably in a cloud environment. So just by way of, Jupyter Notebooks have become an important and really useful and really important tool in the scientific computing space over the last few years. This is one of the first places that we can help somebody actually do their first leap and get outside their laptop. We can take a workload pretty comfortably from a Jupyter Notebook on a laptop and put it into the cloud, and we can give access to, we can give people access to a server to go from a laptop to a server. They can go from a laptop to a cluster. We can give them GPUs if they need it. We can give them a much bigger environment than they normally can get. And then there's some other folks who are doing some really interesting tools. So this is a thing called Pyren, this is another way of getting that immediate scaling factor, and it also works inside a Python environment. What these guys have done is, it's work that's done by the Berkeley RISE Lab, which is an organization at Berkeley University that we support. What they've done is they've actually worked out how to map Python functions, very parallelizable Python functions in a user's code, and map them into Lambda functions in AWS. So they can then, so really it's AWS that's actually doing the scale up. So I'm going to get Ralph to show us that in action, because this is pretty neat stuff.
Okay, so what I have done before, and that's just a couple of minutes of work, is I launched a server on AWS containing a Jupyter Notebook. And the easiest way to do so is pick one of our deep learning AMIs as a basis for that server, launch it. Then you have to do 2 small configuration steps, and after that you're able to SSH into the server and access the HTML front end here. So that's really like, let's say, 5 minutes until you are at this point. And what we're going to do now is, so a Jupyter Notebook, for those of you that have never seen one or used one, it's more or less an interactive Python interpreter in that case. And the nice thing about it is that you don't only have your Python code in there, you can also add some documentation, as you can see. And so what we are going to do now is, we will import the Pyren library. And just by hitting Shift Return, we can execute that tiny piece of code. So we imported that library now. And the next step is, maybe I'm gonna a little bit larger. The next step is to define a function. It's just a very simple function. We just want to demo the library here. And then we're going to call the function. So we have the parameter 5 that we give to the function, and hopefully it's calculating 12 as a result here. So that was pure Python right now. Now we're going to add the magic of Pyren. And for that, we're gonna instantiate an executor, a Pyren executor, and we're gonna give the parameter and the function to that executor. Right now, there's not very much of a difference. It takes a little bit right now because it's the first time that that we started the whole thing right now.
And so what's actually happened is Pyren has actually taken the function and the guts of the function and pushed it out into the cloud as a Lambda function. So it's deployed a Lambda function into AWS. So now if we want to call that a really large number of times, we can actually get the cloud to run it in a massively parallel fashion. And so then you've actually got quite a lot of parallelism happening inside a notebook almost for free.
Yeah. So, and we see the result. This time it's 13, just to show you that's something different that happened. And maybe at this point, so what happened is that Pyren basically fetched some kind of runtime environment, put our code, our function into that runtime environment, then sent it, that runtime environment to a Lambda and executed the Lambda. And this is done asynchronously, and we received the result by getting the result from the future. Maybe a few words on limitations. Since we are working on Lambda, There's obviously one limitation, that is the overall runtime of our jobs. That might be, that is 5 minutes. And the second limitation is that by default, you cannot run more than 1,000 lambdas in parallel. And there's another limitation that's not caused by Lambda, but by Pyron, which is that you will have some overhead. So this packaging of the runtime environment and sending it out might take something like 15 seconds. And so what we are going to do now is, instead of just giving one parameter, we will give a whole list of parameters to Pyron. So what happens now is that Pyron will send out 100 instances of our function with the different parameters to Lambda. And so we're going to run in parallel now. And now I'm just going to tweak our function a little bit. I want to make it last a little bit longer, so I'm adding a sleep. And still, maybe I'm going to skip that one and just go to the massive parallel one. And now I'm going to launch 3 times 5,000 versions of our function. And just to show you that there's really something happening, we can go over to our AWS console and have a look at CloudWatch. And as you can see already, so we are already at 87 invocations right now. Concurrency is still at 51 executions. So that's still our first call with about, I guess it was 100 instances or 100 parameters that we send out. And if we wait a couple of seconds, then it will ramp up because it will reach our 5,000 executions.
So if you're doing a bunch of work, one of the other examples, where we see this stuff happening is large matrix multiplies. If you're doing a lot of mathematical work that involves, essentially solving AX plus B, AX equals B, and doing large matrix multiplies, you can essentially send a really large pair of matrices out into Lambda to have them multiply. This is something that usually binds up a laptop or a desktop, for quite some time, depending on how big the matrices are. You get this done just in massively parallel. And this is actually something that works. It's really nice. It's a nice workload for this kind of environment. It's a really nice workload for Lambda. And it also allows a researcher to just get busy. Look at that, 558 concurrent ones. It allows a researcher to just do that massive jump in terms of scaling the performance of their code or the size of the data pool that they're analyzing really, really quickly and really cheaply without actually having to know any MPI, right? So you've actually prevented them from having to even need to learn all those skills about using an HPC cluster or programming NPI, which is a good thing.
And maybe there's just one thing that I want to add. Maybe you remember there was a small diagram in the lower left corner of the last slide you have seen. That diagram just showed how much computational power you can get by using Pyron. Maybe you can see it again.
Right.
And you're able to reach, in peaks, 40 teraflops. And that's, maybe a few people remember that, about 15, 17 years ago, we had a supercomputer. The #1 supercomputer in the world was Earth Simulator, and that one had 38 teraflops. So we even beat that one, which was the #1 supercomputer 15 years ago with Lambda right now.
So that actually means that somebody can use a notebook to do really, really big scale stuff. And down at the level of an individual researcher who's trying to do some of these things, this could be the breakout moment for getting their workload out of their laptop and into the cloud, quite literally.
So we had that.
Are we done with that one now? Okay, cool. So the other thing that we also, the other task that we've got to focus on is actually making cloud easy to use for researchers. One of the things that we're totally aware of, and I come from this research environment as well, is that researchers are not professional IT people. So most scientists are, awesome Fortran programmers or actually awesome Fortran hackers. But we're not typically professional IT people. So talking to a researcher about DevOps and all those other kinds of things is usually just a whole bunch of confusion. Trying to work out how to set up a VPC inside AWS so that they can get access to the machinery they want is also kind of tricky for them. So one of our partners has actually got really good at this, and it's a company called Ronin. They're a startup company coming from Asia, and they've basically worked out how to take an awful lot of this and turn it into an awful lot of this, into an interface. So I'm going to give you a quick tour through Ronin for a few minutes so that everybody can, you can get a bit of an idea of the kind of stuff that it's possible to do. So let me just make sure that Ronin still loves me and I don't need to log back in again. Beautiful. So the way that Ronin works, instead of actually looking at the cloud as being the end result, it actually zooms back into the user's sphere. And so Ronin thinks of everything in terms of projects. So you're working on a project which might be the Mars lander, or it could be a new Atari chipset, or any number of different things. So, and then the projects themselves have resources. Some of those resources are servers, some of them are hard drives, some of them are backups, some of those resources are people. And then there's also a whole lot of other stuff, and maybe it's a little... Let's see if it's big enough to see. Is that visible? Yeah, just. The other things that you also have as part of a project is you need ways of documenting stuff. So you need wikis, you need collaborative tools, you need stuff for being able to put documentation about a project and put it out to the public and blog posts and so forth. So the Ronin guys have thought of all of that, and so they've actually integrated all of the Atlassian stack, the Atlassian collaborationware stack. So here we are in our dashboard, and one of the other cool things, and this actually solves a big problem for most researchers too, is most researchers are always afraid of leaving a cluster turned on in AWS and discovering that they've spent all their budget in a weekend. It's an irrational fear, but it's a fear, and we have to, we're always trying to figure out different ways of helping folks understand how to beat it. What the Ronin guys have done is actually built a budget in. So every project inside Ronin has a budget, and you can actually see how all of the resources you're using are tracking against that budget. Right? Now, the budget, of course, can be changed over time. Nothing is going to automatically shut off when you hit the budget, but what you will get is you actually get notifications as you progress through the budget over the course of a month or over the course of a year, and you get notifications telling you that you're at 25, 50, 75%, that kind of thing. So that by the time you actually get to the top of your budget, you kind of were warned about it well in advance. And then it gives a human the chance to actually intervene to decide what do you want to do. Well, it may be that you've been running this particular workload for a month and you've got 10 minutes worth of execution time left before you're going to get the results out. You definitely don't want anything to be shut off automatically there. And so it gives a human the ability to actually intervene in an intelligent and thoughtful way. But the other good thing is it also gives the humans that are actually managing the site the ability to actually see all of the projects and how they're progressing against budget. So in this administration screen, we could actually go and do a sort based on who's got the most left or the least left in their budget. So at a campus-wide level, we could actually be looking at all of these projects and saying, well, these 15 projects are doing fine. This last 3 here are a problem. We better call the scientists that own those projects and actually talk to them about whether or not their budget was meeting what they set out to do. Anyway, so every project has a dashboard of its own, and a user that's associated with a project will only see the projects that they're aligned with. Projects have metadata, and that's one of the other really important things, because if in 2 years from now you're actually looking for that machine image for the Mars project when an intern was visiting from somewhere else, actually having that metadata to be able to search is really powerful and profound. So pretty much just like a spotlight search bar up here. Anyway, when we go to create a machine, this is actually one of the coolest and neatest parts of Ronin. We can, a researcher can actually get in through this interface and actually spin up a machine. And they could be spinning up a machine based on some predefined project packages. So you could have a whole bunch of workloads that are specific to the Mars project stored in this folder so that people can get stock images and run stock workloads that are associated with the project. They can also contribute to that library. And so that's an incredibly important part of the collaborative effort. Or they can pull from some of the standard images that Ronin provides. So if we wanted to build ourselves, say, an RStudio server, then we just basically start off there. We need a name for it. I'm going to call it R. And just that. Ronin's actually done about 15 different things through the AWS API to get to this point. And so pretty much every button you click on in here does something pretty interesting for you. Now, if it's an RStudio machine, I may want to start off on, say, a medium general purpose 2-core server while I'm getting my code populated into RStudio, testing out some of the models, just making sure I've got everything right. Later on, I can upgrade, right? And so I can go from a 2-core machine to a 128-core machine if I wanted to, and then, of course, back down again. And so it actually means that you can start to expand and contract the computing to fit the workload that you're working on, but more to the point, fit the cycle, the stage you're at in the development or the execution cycle as well. So anyway, so I'm going to pick like a small machine here. The last thing I need to do is talk about storage. I'm going to go, I only need, a relatively small amount of storage. You'll notice that each step of the way, it's also telling me how much each of these items is costing me, right? So that if you are the person who's paying this budget, you kind of know what impact you're having on the budget. And then there's some other tools I'll show you in a minute for actually getting all of that under control. So I'm going to launch that now. It's actually just going to see what gives me offer of which keys I want to use to log in later. And off we go. So now it's actually off launching the machine. And I'll go back over to the other part of the dashboard, and I'll actually see the list of all of the machines. So here are the 3 machines that I got running inside my project right now. This one's stopped. It's actually turned off. This was a machine learning ML workload. It's the Amazon Deep Learning image. And then I've got another RStudio server here as well. Now, while that's spinning up, I can get access to it. I could straight away just log into this machine now because it's green and it started. Just going over here, and by the way, we can also see, so you can see from there that this machine is going to cost us $21.32 per month. Plus a bit of storage, and the current total cost is $35. You'll notice this little button here. It's saying make this $7 per month. Well, that seems like a cool idea, right? Make this cheaper. That's almost a one-question IQ test. So if this is a single instance machine that you're actually doing interactive work on, it'd be a good idea to shut it down when you go home. Most people won't, because if they went through, say, the standard AWS console, it may well have taken them 2 hours to work out how to stand up a server, right? Remember, they're a scientist, not an IT person. So if they've got to this point, we now have the flexibility of being able to turn things on and off pretty quickly. Why not just say, well, basically we're all business. We work sort of 9 to 5. Now, if I take out Saturday and Sunday, because whilst I'm dedicated to science, I'm not that dedicated to science. And Monday is usually a pretty busy day with meetings and inbox clearing. So now that I've done that, now I've got my costs down to $4, right? And so I can actually save those changes. And now what's going to happen is a Ronin will start that machine up at 9 o'clock every morning for me. It'll shut it down at 5 o'clock in the afternoon for me. And more or less, I'm not even going to notice if I'm pretty much just working between those hours. So this is a really good way for particularly scientists who's very, very frugal with their budget of actually maintaining pretty good control of that budget and driving it to really squeeze out the very, very maximum that they can do. The other thing we may want to do, let's see, like on our machine learning thing here, we may actually have decided, well, actually, we're ready to scale up to something bigger than a T2 large, right? So we've got our code into our RStudio or into our Jupyter Notebook. Everything's looking pretty good. We're kind of just, everything's right. We've staged it, we've tested it. Now what I really need is I need a honkin' big GPU machine, and now I'm ready to do the upgrade. And so now I can change the machine type, and I'm now upgraded. And so the next time I launch that machine, it's going to launch on a P2 8X large. I've now got my environment ready to run. I can scale up straight away. And likewise, when I'm done with that, I can shut it back down and then change the server type again to a T2 and get back to just looking at my code or looking at the results without having to be thinking about the cost of the machine underneath. So there's some very cool tools in here. These guys have made a lot of stuff really easy. They've come up with the concept of backups. And one of the nice things is you can back up a machine and then share those backups with other people, right? So you can, and it's essentially, this is just taking an EBS snapshot of the machine, but it gives you the ability to share those EBS snapshots or turn them into project archive workloads so that other people can come along and use them later on as well. So anyway, there's a lot more to show here. It's a pretty complex product. But actually what's really cool about it is this is basically aimed at getting an end researcher using all of the stuff that's available inside AWS in a really fast consumable way and being able to do some really pretty complex things pretty quickly. Anyway, so I'll get off that. The last thing to say about Ronin is it actually runs all of these workloads inside your own AWS account. So if you've actually gone and spent an awful lot of time, like let's say actually perhaps you've got some sensitive data that you're working with, you might be working with genomic data or some other kind of regulated, controlled data, right? Data security and privacy is of paramount importance. So what Ronin does is it's actually orchestrating stuff inside your own AWS account so that you can go and actually work with AWS. You can get your favorite solution architect to come and help you do a VPC engineering workshop where you design your networking infrastructure inside AWS to be super, super secure with firewalls and all of the rest of the stuff that you need to protect it. And then you put Ronin inside there, and so your users have now got access to a tool to be able to exploit all of the power of the cloud, but Ronin now becomes one of the elements for enforcing your security policy. It'll prevent folks from taking data out. It'll prevent folks from treating data badly or endangering their own data sets. And that's critically important. Anyway, so Ronin is one of those cool tools. Nextflow is another tool that's coming along that we're super excited about. Nextflow is an open source tool produced by a research institute in Barcelona. And of course, an organization of open source workers around the world. Nextflow actually solves the problem that if you work in, particularly in bioinformatics, if you're in an area that's very heavy with workflows and pipelines, workflows and pipelines frequently look like this. This is an actual real pipeline for doing a genomic analysis in a metagenomics environment. Each one of the nodes in that graph is an actual executable workload running inside a computing instance. So what Nextflow actually does is it helps you sort of exploit having all of those bits of code packaged up inside Docker containers, and then it orchestrates entire pipelines, and then also, more to the point, makes those pipelines shareable. So if you're a researcher and you want to be able to share your work and iterate it with a researcher at another institution or across the hall, you can be sharing a pipeline and developing on that pipeline as though it's just a machine that you're sharing with them or a hard drive. So these are all pretty important techniques. And then the last thing we really want to get to, we want to get back to talking about our HPC cluster that we built. And we've got a few minutes left, so we'll do that. As I mentioned earlier, one of the most important things that we can do is to lift the lid off the data center limits. When your problem is that you're trying to solve for is that one on the left-hand side, you've got a fixed capacity piece of infrastructure and you're trying to work out how to squeeze people into it, and quite often you have to bend their workloads out of shape to get them to fit. It's actually pretty relieving if you get into an environment where those limits don't exist. Then it actually means that most of these researchers can come and go from the facility at their own pace. The other cool thing about this is, this is using just the same number of core hours. It's just that instead of sequencing it in terms of what works for the facility administrator, where we can fit you in this month, and that may mean we can only fit you in on the last day of the month, what it means is that it actually, the workflows start to happen at the speed of the researcher. If you look at the scientific world at a sort of a large scale perspective, the computing costs for science is really a rounding error in science. The biggest investment that Germany has in science is actually in the scientists. And so it actually makes sense to try and work out how to get the IT out of the way and make it flexible. We can do this. We can take away that limit on the data center because we don't really have these limits in many respects. Quite often, the spare capacity that we have running in one of our regions is larger than many countries' actual capacities. Right? So that's a hugely interesting thing because it means that your research can, if you've got a research workload and you want to double it, quadruple it, or multiply it by 100, you've got the flexibility of being able to do so. And you can do it for short bursts of time without ever having to own any infrastructure. So it's another big benefit of science. So I'll hand over to Ralph to talk about the cluster that we just built earlier and we just ran a job on. It comes from a European company called Alsace Flight. They're based in just outside Oxford in the UK. It builds what is a canonical normal HPC cluster, but it builds it with cloudy characteristics. I think we mentioned earlier that the number of compute nodes can expand and contract to fit the jobs. The types of compute nodes can change. And then more to the point, and what I think is particularly exciting, is that when you actually spin up one of these clusters out of our marketplace, right? So think of that as the app store for the cloud. When you spin these up out of marketplace, when the cluster comes up, you've got access to 1,500 scientific codes ready to run. And so, again, it's almost like a supercomputer center in a box. So,
okay,
take it away.
So we're a little bit over time. I just want to prove that something happened in our cluster. So let's see. Okay. And so let's first have a look at our queue. And so it's empty again. So something must have happened. And what we're going to do now is we're going to open a GNOME session into the head node and basically start a little bit of a visualization just to make sure that what's that? Maybe so okay.
Hang on, is that there we go.
Oh, it's not my notebook, so okay, and here we are.
So this is something you can't do on, like if you wanted to get access to the national supercomputer facility, they're not going to give you access to a console. So immediately you're doing something that you couldn't do in any other way. You're getting a graphical console on an HPC cluster.
What's it called? We are in the open.
No. Paraphone. You want Paraphone, right?
Okay. So basically, here we are. So we are working on our results right now, but we are really out of time. So let's just.
By the way, we are really not CFD professionals, so.
So what we can see here and what we calculated on, by the way, is how wind is flowing to cities, and that's the model of the city right now.
We can start adding layers showing our wind, showing the turbulence and the wind effects as the wind flows around the building. This workload is This workload is actually in use by real people doing real useful things. It's not a demonstration workload only. The fact that the cost of doing a CFD model of the wind flowing around a bunch of buildings in a city is now something that you can do for $1.75 an hour in the cloud actually means that architect firms, when they're designing buildings, actually can do all of these simulations in advance now. And they can simulate the turbulence effects down at street level of dozens of different building types and shapes and sizes, and actually test them all out before we go and build a building where we may end up making a big mistake. So,
yeah, and we have all seen that in real time. Just remember, I started the cluster at the beginning. We submitted the job at around about the middle of the talk, and now we are ready to view the results, and there's no hidden activities in the background. That was real time, and that's how fast it is to spin up a cluster. And that was just 4 nodes, but let it be 10 nodes. It's just the same amount of time. Let it be bigger nodes, no difference. So
we can be clever. We could actually push all of the jobs into the spot market, into the Amazon EC2 spot market, so that if you want to run the workloads in the middle of the night when EC2 is super cheap, you can do so by just basically changing a flag on the cluster creation. So you could have different partitions. You could have a spot market partition, a real-time one, etc. Here's the vast number of different packages that you could have installed. So if you're using different scientific codes, anything like if you're using Pandas to do data analysis, or OpenFOAM, if you're doing a whole pile of bioinformatics, there's hundreds of bioinformatics tools. And so you can actually just have these things installed literally in minutes and have a cluster that's totally repurposed on the fly. So I think that's it for that last demo, right?
Yes, weird.
Cool. So once you actually start to think about the idea of a HPC cluster or a piece of infrastructure as a bit of code, or as something that you can spin up using a shell script, you can start to think of some other really interesting ways of doing it. We could have another pipeline, and this is a pipeline at a much bigger scale, where we're taking some data coming from, for example, a satellite that's orbiting the Earth, taking photography of the clouds and the atmosphere and the ground and the oceans and the forests. And we could have a cluster that's actually just built for cleaning that data as it's coming real time from the satellites. We could take the output of that and then actually spin up another cluster that could actually be a bunch of GPUs with a machine learning algorithm on there that's actually going to be trained using that data. And then yet another stage, which can be just piling on different layers of analysis. So once you actually start to think about it that way, you can imagine that you could do some pretty interesting and weird things. But most of all, you can start to iterate your science much more quickly. And the iteration is key. That's what's going to get you to your next discovery faster. I guess the last few things, a lot of HPC and a lot of scientific computing is sort of embedded in this part, kind of old-fashioned era of big batch queues and so forth. We really see the need to get away from that. The humans are the people most in need of help right now. It's not the computers. A 3 or 4% faster CPU, or even a 30% faster CPU, is actually not the thing that's going to drive the change in science and the research outcomes. It's actually helping the humans make better use of that stuff that's around already. That's where we see the real hockey stick happening at the moment. More than 80% of the research community never touches a cluster. So if we can take that 80% and help them scale their science 2x, 4x, 10x with really simple tools that they can get access to right away, we can have that big impact. It starts by taking an iterative approach to the software as well. So we've seen a few really cool examples, but they're by no means the end of the story. So I think, Jana, do we have copies? We don't. Okay, so you can get a copy. The URL may be a little hard to read, But aws.amazon.com/RCP for Research Cloud Program. So we've got this book that explains our view of how we think research can be done in the cloud, and it's got a huge catalog of tools from partners and open source groups and so forth that are actually already supporting it. We would love to hear some of your questions and love to hear some of your thoughts. So thank you, and thank you, Ralph.
Yeah, thanks.
Awesome. Hey. And I think it's time for drinks.
Everybody's going for the bar.
Thanks for attending, everybody.